Hi, my name is Arthur Zhang, and today I'll be presenting our work towards robust perception in urban environments, the UT Campus Object Dataset. First, I'd like to thank all of our collaborators for making this work possible. We begin by motivating with this following example. What path should the robot take to turn right here? Traditional methods may choose the purple path to stay further from obstacles, or the blue path for the shorter distance. However, we believe that because the pedestrian is reading the sign in this scenario, the robot should prefer driving the green path as to not block the pedestrian. In this next example, we ask what path the robot should take to cross the shared road. It can either take the purple path, going behind the dynamic objects, or the blue path. For this example, we argue that taking the red path would put the robot to block the dynamic objects, and therefore it should take the green path. From these examples, we argue that richer context-aware robot navigation requires situational awareness in dynamic environments. However, existing urban robotics datasets lack this object and terrain annotation diversity to support this behavior. You may be tempted to ask if we can just leverage large-scale autonomous vehicle AV datasets for object-level understanding on campus. However, we find that there is a significant performance gap when doing this because of the large sensor and viewpoint differences between urban robots and AVs. Here we draw the urban robot that we use, an autonomous vehicle to scale. We also show in our paper quantitatively that there is a significant performance gap for object detectors trained on AV datasets deployed zero-shot in urban environments like Koda. Therefore, we present Koda, the largest multimodal annotated urban robotics dataset, with 1.3 million 3D bounding box annotations for 53 object classes, and 204 million annotated points for 24 terrain classes. We collect our dataset with the following setup. We drive a ClearPath Husky with the 128-channel 3D LiDAR, stereo RGB cameras, multiple RGBD cameras, and a 9 degree of freedom IMU. We ensure consistency between our 3D LiDAR points and stereo RGB cameras by hardware synchronizing them. For all other sensors, we also record their raw timestamps compared to the timestamps for our synchronized sensors. For each data collection sequence, we include a calibration ROS bag with all sensor modalities, and show an example here of what is contained in the ROS bag. We qualitatively demonstrate the quality of our synchronization and calibration quality between the 3D LiDAR and cameras by projecting the points from our 3D LiDAR onto the stereo RGB camera shown here, where the color denotes the forward distance from the camera. Note that colors on the same object tend to have very similar colors, indicating good calibration. We collect our dataset over 5 geographic areas with distinct features, here showing them color-coded on the map of UT Campus. We select each of these geographic areas for the following unique attributes that they bring to our dataset. These include hybrid traffic areas, open classroom spaces, cafeteria and dining areas, road and street areas, and library study areas. We repeatedly traverse each of these geographic areas under different lighting variations, weather conditions, and viewpoints for additional scene diversity. In total, Koda contains 3 rainy, 7 cloudy, 4 dark, and 9 sunny sequences. We also perform quantitative scene diversity analysis of each sequence in our paper. Here we qualitatively demonstrate the scene diversity with respect to weather and lighting. In the second row, you'll observe that the robot is observing the exact same scene under 4 different weather and lighting conditions, those being sunny, cloudy, rainy, and dark. In addition, we qualitatively demonstrate the viewpoint diversity as well. Here shown in the left example, observation of the circular statue from the front and back view. To annotate our data set, we worked with DeepinAI, an annotation labeling company. To start, we draft an annotation guide to make sure that we understand the requirements of our annotations. We provide these to the annotation and quality assurance teams. Next, we gather our dataset and send the point clouds and corresponding RGB images to annotators to annotate. Finally, we work with the quality assurance team and our internal review team to ensure that all annotations meet our quality standards. Next, we will talk about the annotations in Coda. Here we show the number of bounding box annotations per object class. We note the following objects here that are static and are useful for situational awareness. In addition, we also note dynamic objects that are also useful for this case. Here we present a plot of the number of object annotations by class for each weather and lighting category. Note that not all categories are disjoint. For instance, objects that are annotated under rainy conditions are also counted as cloudy. We note that there is significant diversity across weather and lighting conditions for many of the object classes in our dataset. In addition, here we present the proportion of each annotated terrain class among all annotated points in CODa. And here we show a visualization of these annotated terrain points from the 3D LiDAR projected onto the RGB image and include a legend of the corresponding semantic class for each color. Finally, we provide globally consistent pseudo-ground truth poses for sequences in CODa. Here we show a video of the map reconstruction of UT Campus from 3 routes using our pseudo-ground truth poses. We provide a full explanation of these routes in our paper. Finally, we leverage the unique characteristics of CODa to conduct the following quantitative experiments. Question 1, we'd like to understand how well do object detectors trained on AV datasets perform on CODa. For question 2, we would understand how the object detection performance is affected by differences in 3D LiDAR resolution. And finally, we would like to understand if pre-training on CODa improves cross-dataset object detection performance on existing urban robotics datasets. For the later experiments, we will use the bird's eye view object detection metric, where we consider an object as detected if the area of overlap between the ground truth and predicted bounding boxes are greater than a predefined threshold for each class. For the question 1, we show here a table of the bird's eye view object detection performance on CODa using different domain adaptation methods. In the first column, we train a method on the train set of CODa and evaluate directly on CODa, noting this achieves high performance. We also pre-train on AV datasets and test zero shot on the test set of CODa as well, and notice that there is a significant performance gap. Next, we fine-tune models that are pre-trained on AV datasets on the train set of CODa, and then evaluate on CODa as well. This achieves significantly better performance. Finally, we conduct a test using a state-of-the-art unsupervised domain adaptation technique from models pre-trained on AV datasets to CODa. And note that performance actually decreases, which is consistent with other findings that try to apply this method to 2 very different domains. From this experiment, we observed that 3D object detectors trained on AV datasets tend to perform poorly in urban environments like CODa. In our next question, we seek to understand the effect of sensor resolution differences on object detection performance. Here we show a table of the bird's eye view object detection performance on different train and test LiDAR resolutions. In the left column, we train on CODa downsampled to 16, 32, 64, and 128 channel LiDAR. We then test on the test set under this range of downsampled point clouds as well. We note that performance is maximized when the train and test sensor resolutions match exactly. Furthermore, performance gradually degrades as the sensor resolution between train and test differ. We therefore conclude that 3D object detectors are highly sensitive to differences in sensor resolution. And thus, we release pre-trained 3D object detection models for 16, 32, 64, and 128 channel LiDAR resolutions, and recommend that users select the model that's pre-trained on the resolution that most closely matches their sensor setup. Finally, we seek to understand how well pre-training on CODa generalizes to existing urban datasets compared to pre-training on AV datasets. We observe here that pre-training on CODa outperforms pre-training on AV datasets in all categories. Furthermore, it does not fall significantly behind pre-training on JRDB and testing on JRDB. In addition, we note that CODa contains almost 4 times fewer pedestrian labels than all other datasets shown on this table. We therefore conclude that pre-training on CODa outperforms AV datasets in 3D object detection on existing urban robotics datasets like JRDB. We further show qualitative results of this performance. In the left, we train on CODa and test on JRDB, which is what's shown in the point cloud, and on the right, we pre-train on Waymo. We also denote ground truth boxes in red and detections from each model in green. Our model that's pre-trained on CODa has far more true positives and far less false negatives than the model pre-trained on Waymo when evaluated on JRDB. Thank you for listening to my presentation, and for more information about CODa and how to download and use it, we recommend you check out our website, which has a live demonstration of point clouds and annotations in CODa. Furthermore, we provide a QR code for the archive preprint to read more about our quantitative experiments and qualitative experiments. Finally, we provide a QR code for the development kit to download the dataset programmatically and visualize the dataset. Furthermore, you can also download the pre-trained models from our website as well.